today to open the second day of the CU conference. In the first plenary of the day, we'll be hearing about SDG 7, clean and affordable energy for all. It is a pleasure to present the chair of this morning plenary session. She holds a PhD in applied physics from the University of Linköping, Sweden. She's a pioneer in the research on organic solar cells in Brazil. She authored more than 100 papers that were published in high-impact publications. She is the director of the Nanostructured Electronic Devices Lab at UFPR and the Vice Dean for Graduate Programs at UFPR. Please welcome Professor Lucimara Estos Roman.
Yeah, it's a pleasure. Good morning, everyone. Attending our CU Sustainable Development Goals at Federal University of Paraná. It is my pleasure and honor to welcome Professor Fengling Zhang from the Department of Physics, Chemistry and Biology at Linkoping University in Sweden. Professor Fengling Zhang has got her Bachelor of Science degree in Physics in 82, Master Science degree in 85, and her PhD in Solid State Physics at Shantung Institute of Physics and Chinese Academy of Science in 1998. She has supervised PhDs, postdocs. She has more than 107 publications with more than 14,000 citations with age index 64, which gave her many academic awards. 2014, 2015, 2016, she was nominated as the world's most influential scientific minds by Thomson Reuters and Material Science. In 2018, nominated as one of the global highly cited research by Plenary and Prof. So it's really an honor to hear about your research, Professor Fengling, and I welcome to this plenary. Today she will present the plenary talk on the affordable and clean energy topic. So welcome, Professor Fengling.
I can start.
Yeah, you should. Yeah,
I'm not sure if I can control it. I think I couldn't start.
Maybe
Anna.
You can help us.
Okay, I'll help. Just.
The video.
Mm-hmm.
I couldn't start it. It says I can't start video because the host has stopped it.
Yeesh. And I think you are the one, maybe, or from Aptor. We are going to fix Fengling.
Just a second. I'm sorry. Professor. Oh. Okay.
Okay, now you can see me.
The presentation, yes, but you not yet.
So I saw the
cannot start without seeing you.
Yeah, stop. It's a bit strange. Why? I still couldn't.
No, it's working. Yeah, good.
Sorry for this.
No problem. No problem. Yeah. Good morning, everyone. It's my great pleasure to share my recent works with all of you. As in my title, actually, I start working with OPV for more than 20 years. I just came when Lucimara defended the same day, actually. So I extend my work a little bit from OPV also to the energy conversion and storage. So now I will start share my screen for the partition. Can you see the screen now?
Yes, I can see the screen.
Okay, so it's in partition mode, right? Can I start?
Yes, Professor, you can start.
So, yeah. Now is my first slide, show you the title and where I'm from. So, how can I just, now.
Okay.
The outline. So today I would like to first briefly introduce Sweden because we are far away. Maybe not so, for you, some of you maybe not so familiar with Sweden. And then I will give the presentation on 3 topics or 3 kind of device. First is PV for the solar energy conversion, and the second is hybrid capacitor for storage. Then the third part is integrate PV with capacitor to make the photo capacitors. So it's for the portable power unit, then followed by the summary. Yeah, the Sweden is far away from Brazil. We are in North Europe. It's a small country. The population is slightly more than 10 million. However, Sweden is a small country, but it's quite famous for the Nobel Prize. I think for we work in the academic, all of us knows the Nobel Prize is very high, highest ranking prize for the academics. So we are also proud of that. Even I'm not originally from Sweden, but I'm still very proud of the Nobel Prize. In about a week, every year, December 10th, there will be big ceremony in Stockholm for the delivery of the Nobel Prize, and also the big dinner for the Nobel Prize laureates. So this picture shows the king of the country deliver Nobel Prize to the people. In Sweden, also some leading industry. I think maybe most famous is Ericsson, leading the technology in information and communication technology. We also have the company working with the home appliance. The ICA, I'm not sure if there is the shop in Brazil, but it's quite popular in Europe and Asia. There are many shops you can find. It's special for furniture and accessories. Then we also have some big company working with aircraft. Actually, this company is located in our city, Linköping. We have also the H&M, it's for fashion retailer, and the Skype for the internet, and also Spotify, it's for entertainment via internet. So Linkoping University is quite young, started in 1975, it's very young. Nowadays, we have the students, more than 32,000, and the employees, more than 4,000. We have 4 faculties and 4 campus also. Campus Vala is the main campus. So all the 4 faculties may have some divisions in this main campus. And we also have University Hospital campus located in same city, Linköping. Then we have 2 campuses located in another city. Campus Linköping is 40 kilometers north of Linköping. So there's a bus traveling between 2 campuses. And we have even small campus in Stockholm. It's for furniture design. So now we will shift to the scientific part. Organic PV for solar energy conversion. We all know solar energy is clean energy, also it's abundant energy. 1.5 hour sunlight on the Earth can be equal to the 1 year consumption of the total, all the world. However, solar energy is low density energy, so we need techniques to make to have the concentrated energy to be useful. Photovoltaic device is one kind of technique based on the photovoltaic effect. The photovoltaic effect means the voltage generated in material upon the material exposed to the light. So when you use solar as a light source, we call it solar cells. So the sun radiates on the PV and then we can get electricity. It's just a one-step conversion. So because the efficiency always is smaller than one, if you involve two conversion, or will be less efficient than one. So one-step conversion is very good technique. Photon in and electron out. Best example is the electricity generated on site. So you see the house nowadays in Sweden, even we are not so much sun in the winter, still people start to install the solar panels on their roof. So OPV is the possibility to make the spacecraft running in the space. So it's very unique applications for spacecraft and also for portable mobile source of power. In like Africa or some remote area, they don't have the possibility to access the grid. So solar power, photovoltaic maybe is the only source for them to use electricity. You can see people put a big effort to try to improve the performance of the different kind of material PV cells. This figure shows the PV efficiency from different materials. The most efficient, of course, is still silicon crystal, single crystal. So the top one actually is the concentrated efficiency. Then they can get about 40%, 47%. For the multi-junction, like tandem, it's also about 30. For single crystal, it's between gallium oxide between 27 to 30. So we are working with this new emerging PV materials. So you can see the efficiency is still lower than the mature inorganic counterpart. But the people still interested in that is because some unique advantage of this kind of materials. Anyway, the PV industry is quite developed quite fast. You can see the increase is very rapid. So from year 2000 to 2019, so about 20 years, you can see already the capacity increased significantly. Now it's already about 600 gigawatts. So it's an encouraging figure. Now I will focus on the organic PV cells for solar energy conversion. So even the inorganic solar cell is quite mature, but for the production, they consume a lot of energy. And also they involve like high temperature, strong acid. They need a clean room environment. There make the production is very energy cost. So that's the reason organic PV is attractive, because organic PV, they are much simple proceeding to produce device. So like this is a slide to show the unique of the OPV. You see OPV is colorful first. The silicon mostly is black. It's not so beautiful color, sorry. And also they can install vertically because they are not sensitive to the incident light, to the angle of the light incident. And they can be flexible. You can see the curling surface, and also they can make a semi-transparent. We can use it like a curtain. The field actually is initiated by the discovery of the conducting polymers. So before that, we always use the plastic as insulating material. Nowadays, still sorting bag, a lot of plastic things still used as the insulating material. In 1977, so people discovered the polymer, if doping, can be becoming conductive. So these three people got a Nobel Prize in year 2000 for their discovery of conducting polymer. The reason of the polymer can be conducting is due to the molecular structures. They have the single double bond. So if we use some way to excite one electron away from this bonding, then they will form a possibility for conducting electrons. So with that, actually, the material property from electric point of view can be varied from insulating to the semiconducting, also to the conductors. So it's very broad application because of these broad conductivity. For organic PV, we use solution process. You can see the bottle here, different color. That's in the organic, different material with different band gap dissolved in the organic solvent. The band gap determines the color of the solution. For the small area device, we spin coating in the lab, and here's device structure. You see the two electrodes in between, we send with active layer. This active layer absorbing photon and then generate excitons. After dissociate, they will form free charge. That's from the photo-generated induced current. For the large area, we need, of course, spin coating limit the size of the device. So we need other technique for make the film. Here is just an example of blade coating or the roll-to-roll coating for the company. Just briefly to review the mechanism of charge generation and the transport and collection. So for the bulk heterojunction is a key part of the device. We have two materials mixed in this bulk heterojunction. One gives the electron, we call it donor. One accept electron, we call it acceptor. So once the light absorbed by materials, actually here, I just saw donor, acceptor also can absorb light if the energy level is suitable. Once the electron excited after absorbing photons, they will from ground state excited to excited state. Then they form the, actually not free, like a silicon, they are become free charge, but here it's still bonding, but loosely bonding from the exciton. So exciton will diffuse in the bulk heterojunction. If they reach the interface between donor and acceptor, then there are possibility for the electron transfer from donor to acceptor. Then they are still bonding, but they are even weaker bonding, so with larger diameter between them. Therefore, this bonding will be easily to dissociate from free charge carrier. So if they form free charge carriers, they will be diffused or even drift by the field. You can see the electrode, the anode and the cathode, their work function is different. So they will form the built-in potential. This built-in potential will guide the electron and hole to the collection electrodes. So then finally, the electron and the hole will collect back to electrode. So it's the 5-step for the charge generation in the bulk heterojunction. The device architecture, there are quite many different kinds. We can categorize in different way. If we categorize according to the number of junction, there is single junction or multi-junction. Multi-junction, we usually also call it tandem. So like a picture show here, you see the red one is one cell and the orange is another cell. So the two cells step on top of each other. It's the multi-junction and tandem. They can be normal or inverted. This depends on the electron collected on the bottom or on the top. If on the bottom, we call it inverted. If we electron collect on the top, we call it normal. For the transparency, they can be opaque if we have the metal electrode. If we also can make it semi-transparent, then we need to change the electrode. Both electrodes should be transparent to allow the light pass through. The substrate can be hard on glass, also can be soft on the plastic, like mostly common is PET. So that's possible to make the device printing by roll-to-roll. The advantage and limitations. So even the device is not so efficient now, but the advantage still attract people's attention to work on that. First is the low cost, potentially low cost. Nowadays, maybe not low because the material is still quite expensive. The low cost is due to the processing. It's quite simple, and they can make a large area, flexible, lightweight device. And the unique advantage is the material. It's a synthesized material. So countless material already synthesized in past 3 decades. Due to the material is designed and synthesized, therefore, the optical and the electrical properties of the material can be tailored according to the requirement of the device. That's a big advantage of the field. So the limitation, as I saw before, the efficiency, if compared with inorganic material, is still lower, but 18% actually is quite high. Then one thing I would like to point out is 18% is on small area, less than 1 square centimeter. It's very small area. If we upscale or we need a big area device, then the efficiency will be much lower than this number. The other issue is stability, because for the application, stability is a key issue. If the sample, if the device is not stable, it's not possible to make it commercialization. So now the question, how can we further increase the efficiency, or how can we make the even larger device still with acceptable efficiency? Then we need to understand the factors influence the device performance. So actually the people now working in the field, mainly from two fields. One is people synthesize material, synthetic chemists. The other group is material scientist or the physicist working with device. I'm the physicist, so I don't know how to synthesize materials. For material design, they need to think about the band gap should be met with the solar spectrum to absorb photon from sun. And they also need to think about the absorption coefficient. Larger is better. And finally, one of the most important factors, they also should think about the mobility, charge mobility. Because if the charge generated but not transported efficiently to the collection electrode, there are still high possibility to recombine and lost. For devices point of view, the most important key issue is the morphology of the active layer. Means the two material, how they mixed in the bulk heterojunction. This part concerned about the charge generation, also transport. This part depending on many issues. First, the material property, of course, is the most basic issue. We should think about that. But even the material is good enough, we still need to use the optimize the conditions to make a device. These processing conditions, like temperature and the solvent, additive. So nowadays, most popular standard processing condition always use some kind of additives to adjust the drying time, make material have good time to mix each other, or they mix each other. So it's depending on material. For the post-treatment, they also some materials, it's a need to be post-treated with like thermal annealing or solvent annealing to further manipulate the morphology. So after the morphology of the active layer optimized, interfacial layer is also very crucial because the charge extraction is depending on the interfacial layer between bulk heterojunction and the electrode. Finally, electrode, of course, is important for collection. Efficient collection is important at the last step. So today I will mostly focus on the morphology of active layer. So the first part I want to share with you is our very recently work in these 2 years, something like that. It's on the studying of the morphology formation. Because you see as I said, the bulk heterojunction morphology is very important, but it's formed during the solution drying from liquid to solid film. Therefore, actually, we don't know much about what happened, even this drying process is key to decide the final morphology, but still we don't know how to, we are not very understand what happened during this drying process. It's like a black box. Therefore, we are interested to know what kind of parameters more or less control the drying process for further to improve the device performance. So we want to watch the film drying. Then we need some tools to do that. We have the homemade in situ spectroscopy, like showing here. This equipment, we can collect the signal from for the photoluminescence from the active layer, and also we can collect the signal from the light scattering. So you see we have the laser illuminated on the surface during the solution drying when we make the blade coating, and then we alternatively collect the signal from the laser scattering and also the PL from the active layer. With that, we can get the spectrum looks like this. So the broad is PL and the narrow is laser scattering. It will be varied with during the drying. You see the PL quenched and the laser scattering then maybe increase because then they form the aggregation. The scattering is getting stronger. So with this spectroscopy, we can some kind of watching the film drying. So let me choose different what kind of things information we get from these variation. So first, we can monitor if the spectral peak shift or not, blue shift or red shift. So that spectral shift will give us information about the configuration of the active materials in the liquid. And we also can get the intensity of the photoluminescence that also tell us interaction between or in the donor and acceptor. Of course, also interaction with the solvent. So this laser scattering intensity tell us the aggregation size. If they are bigger or smaller, of course, bigger, they give the stronger scattering. If they are smaller, they give the weaker scattering. So with this, we need some system to work with. Then we choose the materials used in the study. We choose we fix the donor and vary the acceptor. We select 3 different representative acceptors. Traditional acceptor fluorines is not so popular now because we have the new non-fluorine acceptor with better absorption compared with the fluorine acceptor. So we also have the polymer acceptor. Polymer acceptor nowadays is also not as efficient as a small molecule non-fluorine acceptor, but they have big difference. Think about the molecular weight. So we want to know if the molecular weight and the molecular structure, how can they influence the film drying. So first, we try to image the Princeton material drying process. So here is the donor material drying image of the donor material drying. Then we can see the PL spectral shift with the time, and or we can say with the solvent evaporate, the PL shift, red shift. We also can see the PL intensity decrease with time, and the laser scattering increase with time. So you see the time corresponding each other very well. And then we also image the 3 acceptors. We can see the difference among the 3 combination. So for the small molecule, no matter fluorine or non-fluorine, they are red shift. But for the polymer acceptor, they are blue shift. And also the light intensity decrease, PL, is different. For the polymer decrease faster, And for this non-fluorine acceptor, actually it's increase bit, then decrease. So these different behaviors give us like a reference for the blend. This is a pure material. Then we will image the recording the numbers from the blend. So we have 3 blend. Then we get the 3 different kind of signals. So these signals give us different information. So some materials we can see for the donor and acceptor in different combination dominate either by donor or by acceptor. It's a bit interesting for the polymer acceptor. They have 2 peaks at after it's drying. So if we think about the drying kinetics, then we can check the drying time. Here for the pure material, we have drying time. Drying time means when they are reached the T1 solution is close to evaporated already. That's till T2 is totally dry. We suppose it's totally dry then. So T1 to T2 is a transition time from liquid to the solid. Then we can see actually the polymer donor and the acceptor always so much longer, time for the drying. And in blend, it's depending on donor acceptor is different. For the small molecules, it's more close to the donor, the time, but for the polymer acceptors, it's dominated by the acceptor. So with this information, we know which one is play key role here. If polymer blend, we also check the molecular weight. So the conclusion from this study is the high molecular weight dominate the drying process. So this is the conclusion from this part of the work. This work published this year. If you're interested in more details, you can read the whole paper to find more details there. Also some supporting information there. So the morphology, of course, we don't know the bulk morphology. We can see the top graph. So the top graph also, the top is the pure material and the bottom is 3 combinations. Still, you can see here, for the small molecule acceptors, it's dominated by donor. And for the polymer acceptors, then dominated by the acceptor. It's due to the molecular weight for acceptor is even larger than donor. So that's the conclusion we get from this part of work. Larger molecular weight determine the drying process and dominate the final morphology. Top graph at least show us this one. So the second part I will show is external dissociation charge generation within the bulk heterojunction. For the charge generation, actually, before I only saw about the donor acceptor, we think about it is a space mix, how they mixed. Actually, there are also another issues will influence the charge generation, that's energy offset. Because the different material, they have different capability to catch the electron. Therefore, this energy offset is a driving force for the external dissociation. That's the reason why the bulk heterojunction works better than a pure single material device, because in pure material device, single material device, they don't have the driving force for charge dissociation. So here also I saw the 3 different situations. When we work with the fluorines, because fluorine is quite a large band gap material. In most combinations, they have enough energy offset for the driving the external dissociation. But the non-fluorine acceptors, they are attractive because they are small band gap material to absorb more photons, and also due to they can be modify the homolume levels to match with donor. So they try to minimize the voltage loss. Meanwhile, collect as much as photon to generate photocurrent. So that's the reason they are very efficient, due to they can optimize simultaneously both current and voltage. However, there are still some limitations. I mean, you couldn't, the trade-off between short-circuit current and the open circuit voltage always hardly to overcome. So when we try to increase the open circuit voltage, we need to decrease the driving force or energy offset. So if the energy offset is too small, then maybe it's not enough to separate the exciton. So like here, I saw the two situations on the right. The right one means in the middle one is reduced HOMO offset compared with the left one. So it's close enough. They are not a very big driving force for exciton dissociation. On the far right one, it's even worse, because in this case, we can see it's energy transfer. It's not the charge transfer, because the exciter energy is in the band gap of donor material. Then we have questions. Actually, according to the traditional opinion, this kind of combination should be not work at all, because it's not charge transfer, it's energy transfer. However, with this new non-fluorescent acceptors, even the HOMO level offset is quite small, still quite efficient cells we can get. So in this case, we compare two situations. We have some collaborators in China, they can synthesize material to control the HOMO level, to make the HOMO level with different range, smaller one or even negative. So that's a part of this work. So in this case, we fix the donor, use PTQ10, and the acceptor use two very similar materials, only slightly changed to keep the energy level, to keep the properties, not so much difference. So you can see the X here can be CH2 or can be an ME. Therefore, you can see the energy level here. It's very close in the orange part. You can see one is 5.65, one is 5.53. For 5.65, they have still have a little bit driving force. But for this JITIN, there are almost no driving force at all, because it's negative offset. So with E2, we make the device. This device at optimized bulk junction means the ratio of donor and acceptor, they are optimized. It's 1:1. Then we get the performance as shown here. For the small energy offset, we get the efficiency, it's 13. It's quite decent actually already. The voltage you see is close to 1 volt. It's quite big with a narrow band gap, etc. For this TQ10 with JITIN with the negative HOMO levels, you can see the efficiency is drop half to the compared with the JITIC. But even then, still we think it's quite impressive, because the energy offset is negative. You should remember it's negative. Then suppose not work at all, but we still get the 7% power conversion efficiency. It's really amazing. Also, the fill factor close to 60 is quite good, and the current 12 or 13 milliampere per square centimeter. That's also very nice number if we think about the energy offset is so small. So then we try to understand how it works. It's hard to understand with such negative driving force, we still get such good photocurrent and fill factor. So then we check the photoluminescence to see the charge transfer if it's efficient. Then we can see the big difference between two acceptors. For the acceptor with the small driving force, the PL quenching is better than this JITIN. For JITIN, we can see the yellow part. It's very obvious. So that means, indeed, the system with the negative driving force, the PL quenching is not complete, means the charge transfer is not very efficient. We also check the lifetime of the exciton. You see the transition absorption shows for the negative driving force, we have the longer exciton lifetime, means they are not easily to separate it. So then we try to standard how come the acceptor's contribution to the charge generation only via Hall transfer. Therefore, we make a device. Actually, we want to make a bilayer device, but the student in Beijing told us it's not possible from the solution processing. The top layer will dissolve the bottom layer. Then we think, oh, it's okay. If we couldn't make that pure bilayer device, maybe we can make the dilute donor device to decrease the impact from donor to amplify the contribution from acceptor. So it's closer to the bilayer. So this way we use the 1 to 10. We only put 10% donor there. So you can see from the device image, mostly the orange part means they represent the acceptor. So the donor like merged in the acceptor C. We hope this way we can add small, decrease the impact from donor, only folks get the information from acceptor. So indeed, for this not optimized stoichiometry, we indeed decrease the efficiency of device. For this one, we get the device performance drop from 13 to 9, and for the TQ, for the ZITIN dropped from 7 now to 1.3. The fill factor clearly much dropped. So the current also very significantly smaller. Then we check if the field will help to overcome the limitation for this driving force. So we check the external quantum efficiency with the bias on the device. Let me see the different behavior for the two systems. For this CITIC, because the driving force is positive, the field not have much for the EQE. You see, it's not a small, it's very small change increase. But for this JITI system, the field so significant enhance the EQE. So that means actually the built-in potential in the device assist the charge separation in the active layer with negative driving force. So that means if the driving force is large enough, then the built-in potential impact is not so important, not so significant. But when the driving force is negative, the energy offset doesn't help to separate the excitons. This built-in potential just step in to take the role to separate the exciton, become free charge carriers. So that's our work to give to identify the built-in potential's contribution to charge generation in the not efficient junction, bulk heater junction. So next part I want to show you is still dilute donor solar cells. But this time we use the, star material in the field. PM6 is the best, almost the best donor so far, and the Y6 is also the best, #1 acceptor. So in this combination, the purpose for us is to illustrate the contribution from acceptor. Because the field actually significant progress is due to this non-fluorine acceptor's contribution for the photocurrent generation and also for the photovoltaic enhancement by aligning the energy levels. So therefore, I may be too slow, I should faster. So here is we make device. We also use diluted structure due to we want to show the acceptor influence instead of donor. So EQE and IV as shown here with different percentage of donor. So here summarized the efficiency of the device I highlight the 10% donor. You see the 10%. Before we make device, we never imagine we can get 10% efficiency by such a smaller donor there. So yeah, this shows the different variation with the percentage of the donor. We can see actually there's like a saturation region. I mean, from 20% to 60%. They are not so sensitive to the stoichiometry. They are quite good. So this transient absorption also shows for the device with 20% and 45% is optimized. It's quite a similar behavior. Okay, so here's the morphology. Shows the domain size different, varied. So here shows the mobility. From this one, we can see actual acceptor is an ambipolar material because they transport both equally for hole and electron. So then we want to know if the charge transport only depending on acceptor. We compare with different kind of insulating materials. Then we figure out still even 10% donor there still take a main role for the transport hole, not much by the acceptor. So it's clarified the acceptor in device mostly contribution for the charge generation and the photovoltaics, not for the transporting hole. So encouraged by this part of work, we also found the application of the low donor device. Because you see the acceptor is nearly, almost the acceptor is a low band gap absorption the long wavelength photons. So if we decrease the donor content, then we can decrease absorption in visible light, invisible part. So then we can make a device even transparent, but still can absorb enough photon to generate current. So here we use the same combination, still PM6 and Y6, but we make the difference of the part work with previous one. We just need the transparent electrode to make the light transparent. So the key issue here is found the good combination for transparent electrode. And there are different parameters to define the performance of the transparent OPV. One is when we are not only concerned about power commercial efficiency, because that's definitely will be lower than opaque device because it's single pass of a photon. Another is average visible transmittance, because we are more concerned about the people's eye, most sensitive to 550, something like that. Then we should enlarge that part transmittance. For the people's not sensitive range of photon, we can absorption more, but this part we should not absorption more. Therefore, we use another parameter to define the performance of the device. It's light utilization efficiency. It's a product of the PCE and the average visible transmittance. So we make different device with different stoichiometry to optimize the transmittance and also the power commercial efficiency. Here I highlight the 20% donor. For 20% donor, the LUE, we get the largest, 2.7. Compared with so far published semi-transparent devices, this number is quite good. It's among the high one. So like showing here. Here I also show the photos. You can see from the photo for the 20% red one, the B, figure B, they are balanced the transparency and also the efficiency. Figure E shows for the when we absorbed, we should not change the color. It should be neutrally decrease the transmittance. So this case, we compare with this one, we see we are not change much about the nutrition of the light. So the next part is the ternary. So far, people almost ignore the fluorescence acceptor. Is the Fluence acceptor will disappear from the field? Maybe it's not, because Fluence acceptor still for transport properties, maybe still some advantage over non-Fluence acceptor. So here's a ternary. We try to how to say synergy the two acceptors to make a better performance device. So this work we did in 2018, collaborated with a group in Beijing. They synthesize material, so then they check the binary. First they check the binary, and then they mix the PCBM with the acceptor, a non-Fluence acceptor. Then they get the efficiency better than either of the binary system. So we try to understand how the functions or how the rules for the acceptor for Fluence acceptor take in the device. So we imaging the bulk heat junction, then we can see if we compare binary and ternary, we see the PCBM actually form clearly like a highway for the charge transport. Therefore, we suppose, so yeah, here we suppose actually PCBM here like highway for the non-Fluence acceptor, they help to separate the exciton, then give the electron to PCBM. So PCBM take it away to the electron. So with this ternary, actually we synergize the two acceptors. They play different role, one for charge generation, one for charge transport. Yeah, I should be faster. So next part is the hybrid capacitor. If we think about OPV, there is one limitation is due to the sunlight. It's not continuous available. So for storage, it's necessary for application. Therefore, we think we are also interested in the solar energy storage. Then we start with working on the capacitor. In Linköping University, we have a group. They work with Maxine. I think maybe you know it's novel 2D material. It's now become quite attractive. So this 2D material, because for PDOT-PSS, even it's a high conducting polymer, but still it's not high enough. When we make this Maxine, we change the different stoichiometry, then we found at optimized geometry, they help to increase the capacitance of the capacitor. So here shows how we mix the film. We mix Maxine with PDOT-PSS, and then we filtration get the solid film. So this film, we can use it as use it for capacitor. So here's a lot of curves to show the CV measurement, and this also so the charge discharge with different current density. I will not go through. I think I have not so much time left. I will go. Here, this paper published also 2018. If someone interested can go to the detail to look at the details. Here I want to show you is how the film look like. This TM shows actually this mix Maxine and the PDOT-PSS make a lot of space between layers. That's the reason they can store more charge, increase transmittance, capacitance. Yes, this is from capacitor. That is preferred from the film. This is from capacitor, make device with electrode. So here's for the different connection, because single capacitor, they are not meet the requirement for the application. So we try to connect them in serial and in parallel. Then we get a different performance. Yeah, this paper, I think this is the last part I will share with you. It's about the integrate photovoltaic with capacitor. It's flexible. Of course, it should be semi-transparent because for the photovoltaic, we need incident light to be absorbed. So here shows how we make the film, the materials, and also the characterization for the how the material film looks like. And this one, so how we, I think I have a problem too. The block a little bit. Okay, now it's better. So electronic properties of this film is still a magazine, another kind of magazine. Here's yeah. Okay. So the transmittance will change with the stoichiometry, and we can see. Okay, sorry. So here shows the optoelectronic property of this film, and then we make a device. We also here also show the conductivity. When we bend it, sometimes the material may be cracked, then the conductivity will be decreased. So this test we check, you can see the conductivity keep quite good, even we bend it after many times and different angles. So this is performance about, oh yeah, there include quite many pictures here because we have to evaluate separately the OPV and the capacitor. Then finally we can put them together. So is it time? Matthias, okay. I just maybe have 1 or 2 slides, so yeah, I should be faster. Okay, it's a bit strange now. It stops. Okay, now. So here just show different active layers. The 3 different colors show different active layer with different electrode. It's quite a lot of work. Here also show the supercapacitors. So you see the device now. The same measurement, but it's on device, not on film anymore. So I won't go to detail here. And this performance also based on electrode. You can see on the right, top right, there's 2 devices actually. It's one PV device, one is capacitor. And this one can illuminate from either side, either from the solar cell side or supercapacitor side or from OPV side. So it's transparent. So I think I should summarize. I prepared too much maybe. So first, I share with you several parts of work. Firstly is we monitored the morphology formation. And the second, we studied the charge generation mechanism in non-French receptor with negative energy offset. Then we studied the charge transport mechanism in dilute donor OPV, and followed by the application, use this result as a transparent, semi-transparent OPVs for built-in PV. That will be have huge application in the future. And the Fengling receptor role in efficient ternary OPVs, we will also demonstrate. Then finally, the capacitor and the capacitor integrated with the OPV. So with that, right? I couldn't.
Yes, it's amazing talk, Fengling. Thank you very much. Yeah, it is, you know, to put the capacitor in the solar cell, it's a dream. It would be really nice to see it in a product a few years from now, I hope. And I love the work about the diluted to understand really how the photocurrent is formed. Okay, the group, very good.
Yeah, I would like to thank the people, collaborator, and also, I think this photo took by you, Lucimala.
Ah, yes, with Lana. This is nice, Fengling. Yeah. Very nice. Yeah, that's true. When I was there, yeah.
So that's a pity you are not here because you took the photo for us.
Yes, otherwise someone from the group is always out of the photo. So I okay, we have one question. Can I make for you, Fengling?
Yes.
It's from Leandro Benato. He asks about the improvement of the efficiency of solar cells. that some works mention the triplet extons. And do you think these triplet extons, they are going to help to increase the efficiency in these OPVs?
Sure. Actually, I have big hope on the triplet, but unfortunately, you see not so many people interested to synthesize material for us. So, I mean, the device is strongly dependent on material. I have a collaborator in China. We have the project collaboration on this triplet, but her background is for the triplet material is for lightning diode. It's not for PV. So therefore, you see, at the beginning of OPV, we only use PPV. That's lightning material. It's not absorbing material. So there's a mismatch with absorption. So they're still, for the triplet now, still is high bandgap material. It's hard, we don't get the low bandgap material to absorb some long wavelength photons. That's one limitation. Another limitation is for triplet, we will decrease the voltage. That's sure. And
but maybe it's one way to go.
Yeah. Yeah, I still not give up. If someone will material, we work that.
Researchers are like this. Yeah. So I don't know if Luis would like to say something. Otherwise, you know, we continue with the event in another room. If you'd like to go to another room, Fengling, it's the link here in the chat.
Okay.
So then it's SDG 7. Then we are going to move to that room now. It's like in person, you know, you change rooms.
So now it's 5. Oh, no, we are 5. Where we are now? We are 5.
So then
I saw there's SDG 7. I saw it. Okay.
Okay. So thank you very much.
Thank you for your attention.
It was a really nice, amazing work you showed us today. Very nice. Thank you.
Thank you. Bye.
Bye.
Thank you all for being here. We now are ending this plenary session on SDG 7 with this amazing talk by Professor Fengling Zhang. And coming next, we have a panel session on SDG 7. So you all interested in clean and affordable energy for all, please go to the link on the chat that I sent to you. And also have a panel session on SDG 5, gender equality, and you can go to the link on the chat as well. Thank you.
Thank you
again.